As part of the design thinking approach, I've mentioned that always be judgmental. I was thinking about it that in my previous videos, I've mentioned that sort of as a fact that when we would like to test our design during design phase, and one of the requirements is an impact requirement, then we can always simplify the problem by having an equivalent static analysis instead of performing like a more complex dynamic analysis, impact analysis, that will represent the problem in order to help us understand how the design behaves so we can make appropriate changes. But thinking about it, it always made sense to me that you can do that, but you have to take into consideration that this is good up to a certain point of if the impact duration, it doesn't correlate with the natural frequency of the system, with the first mode or the second mode or one of the modes of the system. But then I was thinking, well, it makes sense because then it's like having a instead of vibration, you just have it one cycle of this vibration as an impact on the system. But I actually never tested it, so I thought to myself, well, although it makes sense, I have to be judgmental here, and I have to test it. I have to see if it does make any difference to have a static analysis. Is it actually representing an impact analysis? And what happened if the duration of the impact analysis, the profile, fits with one of the modes of the design itself? So I thought it would be a nice idea to test it myself and share it with you guys. What I did is I just loaded up a simple beam, and what I'll do is I'm gonna perform a static analysis, a model analysis, and then two impact analysis. The first one is going to be a normal impact analysis to see if the stresses are equivalent. And for the second impact analysis, what I'll do, I will test it with a profile that match the one of the modes of the system, most likely the first mode, but we can also test it for the second mode to see how it reacts. Since I know that this is going to be my fixed phase and this is going to be my load phase, I know that it's going to be the high stress is going to be here. Then in this case, what I'm doing is just refining the mesh at this specific area. Okay, so next thing is we're gonna select material. For this one, I'm going to select specifically a material that I know for a fact is going to give me low natural frequency of the system, because I don't want to, because I wanted to create a profile that will resonate. So I'm aiming to get low frequencies. So this is the beam. Create a section. So I've created a fixed phase and a load phase. It's always easier for me anyway to have a name selection so I can easily apply boundary conditions. Okay, for the first step, we're going to make it simple. I'm going to create a static boundary conditions fix. We're going to have the surface name as fixed. Cool. Loads. What we'll do is create a load of not concentrated force but surface traction, which is going to distribute the force over the surface. I'm going to select face. What I'm going to do here is, since I assume by looking at the inertia of the beam, I can assume that the first mode is going to be in the Z direction. And then most likely the second mode is going to be the Y direction. So what I'm going to do is I'm going to test the load for the Z direction. And I'm going to do it minus Z, okay? So I'll just give it 100 newtons in the negative direction of Z. That said, the next step, what I'm going to do here is I'm going to have a frequency step, a model analysis. And in order to use it in future analysis, I'm going to use the storage for save. The rest of it is going to be the same, and what I'm going to say model analysis FEA. For the first part of it, what I'm doing is I'm having a static analysis and a model analysis. Okay, and why is that? Because from the model analysis, I'm going to extract the modes. Having the modes, I can then convert the frequency to a time duration. So I can either stay away from the duration of a cycle that correlates with or resonates with the mode, or I can have the impact directly on the duration of the mode. So there was one thing that I've set up and ran the analysis, and it didn't work correctly. And I found out that instead of having the load phases set up correctly, I had fixed phases instead of load phases. So the results didn't make sense to me, of course, because everything was 0. So I went back and I changed it, and now we're ready to go and continue with the analysis. Okay, so let's go ahead and run the analysis. So now at this point, we can see that there's a displacement for the first static analysis. And what we can see here, there's a concentrated stress at this edge over here, this point over here, which state as 11 megapascals. So looking at this is nice. Let's go back to, let's go to the frequency, and we can see here that the first mode is about 73 Hertz. And as my first assumption was, it's going to be on the Z direction, which correlates with this. I don't mind about seeing all these stresses. At this point, even the displacements doesn't really matter. I'll explain it in different video why it doesn't matter, because we are just doing frequency analysis at this point. So first mode 73, second mode 143. Cool. So we have the static analysis and we have the model analysis. We have the first few modes to analyze. So the next thing is, let's see what's the first mode. It's 73 Hertz. And what I'll do here, I'll just convert this to seconds. So having that number, next, what I'll go back, and now we can create the dynamic analysis. In order to actually create an impact, what we'll do is we're going to create an amplitude. Okay, and with that we'll create a graph of time-dependent amplitude, and we'll set the time. If you remember correctly, it was 0.013 of a second as a duration of a full cycle frequency. So that said, if we try to avoid this, then let's make an assumption that the impact was something like 0.014. That was the duration. It was peaked at 0.014 like at 14 milliseconds, and ended by 22 milliseconds. So the whole duration of this impact would be about 22 milliseconds. Okay, with a peak at 14 milliseconds. And then we'll take it by 1 and still set it to 0, and we can plot the graph and see how it looks like. And then we can see here that it peaks at 1. So let's create the next step, which is the impact analysis, and we'll name the first one as impact FEA. And we'll do it the 1 because this one is not resonating. I would like to put it as with a dumping of 0.02. Maximum increments will be 1000, and the resolution, I'll just go with not too high of a resolution, but I will just divide to 10 our resolution, So we'll make sure that we are in a good resolution. And I will take 100 milliseconds at a total, which is technically we're going to have like 100 steps in the analysis. And we're ready to go. So we've created the impact, the first impact. Boundary conditions are derived from the model analysis, and the loads, this is where we add the loads. And we're going to use surface traction. We used surface name and load surface, and we'll of course set to 100 Newton as the static analysis because we want to compare these two. And the difference here that now we're going to use the first graph that we've added as the peak for the 100 Newtons. Press OK, run the analysis, then we'll see the results. Okay, so first of all, let's examine, okay, the results. If you go back to the static analysis, this is the results of static analysis. We have, well, our peak is at 11 megapascals at the edge. This can be singular point. This can be the actual stress. I don't know. At this point, I'm not really interested of exploring this. It's more comparison between different analysis. And I also took another sampling point of where stresses accumulate. And here it says 9.354. Okay, this is a static analysis. So if we look at the results for the impact analysis, red looks very scary here, but if you look at the numbers, which it's close to zero, which means we are starting from technically zero. And then it increases gradually as the load increases. And we can see here that the numbers increase also. Since we incrementing by 1 millisecond and we had it on like the 14th millisecond, the maximum load, then I expect the maximum load to be at the 14 millisecond. And as we can see here, it's equivalent to the results of the static analysis. And if we continue, it just, well, it increases because it's time dependent. But then again, it just increases to almost nothing, which actually is a good result because it makes more sense that it's actually creating that impact analysis on the material and not just giving us the number of the static analysis. So this is actually a good result. I'm not scared that this is different because at the level of 11.2 to 11 megapascals, we're not looking for like the most accurate results, but we're looking for a way for us to estimate whether we need to make changes or not to the design, because we're on a design phase. This is not like a final analysis, so we can use this as a tool. But we can see here it's pretty much equivalent to the results of the static analysis, which is here. So that's interesting. But the next thing is, and what I'll do next is actually let's plot the actual resonating of the system, whether it resonates or not, and how it looks like at the end. We do that by adding history, and we'll select a node, more node, and what I want to do is select, like, let's select this node, and what we want to do is we want to measure the deformation, because this will represent us how the material behaves in terms of rate of resonating. Let's run the analysis again. We've run the analysis again. We'll just make sure that we have the same results. Yeah, so we have the same results. And now we go for something interesting. Let's see how the displacement was like. And we use U3 because this is on the Z direction. And what we say, we get a graph of the displacement. And what we'll see, this is how the displacement look like, including the dumping. It impact, and we see that the results actually correlating with what we're looking for in terms of an impact, because it makes sense that when you hit something, it keeps vibrating in a certain level until it's decayed. And here we see, like, since we do have a dumping on the system, it just gradually goes down. Now we've tested the model for static analysis, impact analysis, but we kept ourselves away from the first mode. And now what we'll do, we'll just create an impact analysis that actually correlates with the first mode of the design. What we do now is we're going to add another graph, and since we know the first mode is let's see, it's about 14, so we'll just divide it to 2 because we want to put the pick in the middle. It's 0.07 and 0.014 is the end of it. We'll just add an amplitude of 1, and then 0.1 is just the whole graph. Let's see how it looks like, as we expect. Okay, so, and then we go back to the impact analysis. We just switch to the different amplitude, and then let's run it again, and we'll see what happens. Okay, so we'll go to stresses. Kind reminder of what we're looking for is about 9 megapascals, and 11 megapascals is the max. And now we're gonna see how the stresses are when it peaks on the impact. My assumption is going to be like anywhere between 7 and 10. This is where it's going to be, because with the increment of 1 millisecond. Then I'll just go straight to 8, and immediately we see the difference in the stresses. And we're on the 8th, and let's keep exploring this. 17, 17.3, 15. So the maximum is at the step number 10, which goes highest to the 17. If we look at the previous results, which were pretty much matched to the 11, it was 11.2. So the change was 11.2 to 11. It was like 1%, like 2% change in the stresses in comparison to 17, which is like, it goes like 60% more in comparison to the static analysis. That concludes us that, well, first of all, the assumption of using static analysis as an equivalent for an impact analysis, it can help us out in the design phase, as long as we are staying away out of the modes of the system. Because now we see that it also confirms that when we are impacting in the duration of which complies with the one of the modes of the system, then it does what it's supposed to do. It resonates, it amplifies. So in that case, static analysis is less useful here. We can still perform static analysis, okay? But then we need to think a little bit differently, taking a little bit of a safety factor for the loads. I would at least increase it by 2, or maybe even by 3 times the load to be safe. But looking at this, it confirms what I was theorizing for using the static analysis as an equivalent analysis for impact, as long as we're staying away from the modes of the design itself. So if you have any comments or questions, feel free to leave comments down below or contact me through LinkedIn. And please welcome to watch the rest of the videos in this design thinking series.